Okay, we are going to talk about the MIP, HPT, and EC or electrical connectivity, and talk specifically about each one of those and how they interact. How we're going to step through this today, there will be a couple slides, just very basic introduction on direct push technology and the logging process, and then we will talk about the MIP probe, the system and tooling, the electrical connectivity and HPT operation and interpretation of that, those sensors. And then we will step into the gas phase detectors, analytes that they can detect, what QA tests that we have and trip times, and we'll understand that a little bit more as we get forward, move into this presentation. And then talk a little bit about analytes that can and cannot be detected, how you can best see if MIP is something that's going to work on your site. So we'll talk a little bit about that, and then have some interpretation of the detector graphs and logs that have been generated. We'll show some varying examples from different types of sites, and then some field examples. So we'll now begin. So here, direct push technologies, basically we're utilizing, it's gonna have, the machine is gonna have a hydraulic hammer, hydraulic rams and slides, and utilizing the static weight of the vehicle. So we're not gonna be doing any rotation, no cuttings or rotary drilling. It's is only going to be advanced in unconsolidated soils. Obviously not applicable into the bedrock formations. So again, where this works quite well is going to be in your silts and clays, sands, gravels, things like that, alluvial deposits, those types of formations. The more dense the materials, tills or hard sands, caliche, it can become more of a challenge in there. And of course, the bedrock materials, it does not, the direct push technology will not work in. With the logging process, we are going to have our probe that we'll be discussing with the various sensors on there. It's going to be in direct contact with the formation, and there's not going to be any pre-existing borehole or anything like that that is going to be lowered into. So we need to be in direct contact with the soil and to be able to make the measurements that we will be obtaining. So here's a picture of the MiHPT probe, and the first sensor I'm showing here is the electrical connectivity dipole down here at the bottom of the probe. And this is the graph that will provide, and I'll talk a little bit more about that in a moment. On the back side of the probe there's a removable screen where we're actually going to be injecting water into the formation, and this is going to be where we're obtaining a measurement of hydraulic, or basically permeability. It's the hydraulic profiling tool. We're injecting water into the formation to see how much pressure it takes to inject that water. And up above the probe, there's going to be a pressure sensor that's monitoring that injection pressure. And then here in the middle of the probe, there's a heated block. There's a couple heaters in here and a semi-permeable membrane. And this is where VOC contaminants can diffuse across the membrane and be brought into a carrier gas and brought to some surface detectors. Here are the added detector channels that we can obtain in these logs. And so with the lithology, along with contaminant mapping, it provides a really good understanding of contaminants that may be there, present on the site, and what their context is. So that's a very important thing to have there. So with the membrane interface probe, we can see it's real-time mapping of VOC contaminants in gaseous, dissolved, and free phases. A little bit more challenging in the super high concentrations or NAPL levels, but we can detect up to those points. Petroleum hydrocarbons, chlorinated solvents, which is the primary type of solvent that we'd see there, as well as you could get methane and other unsaturated hydrocarbons like that. We are able to get this data both in the vadose zone as well as below the water table. And as mentioned, we have electrical conductivity and HPT for our lithology mapping, and we're collecting data points every 15 millimeters. So when all this is put together, really essentially, appears as though there's no vertical data gaps. On the membrane interface probe, how we're getting the VOCs in, again, I said there's a semi-permeable membrane. There's a heated block on there, and when you have VOCs in the subsurface, they can diffuse across the membrane. We have an inert carrier gas, typically nitrogen, that's coming from the surface, constantly sweeping past the membrane, and that will wick those, help to diffuse those VOCs through the membrane into the carrier gas and bring them to the surface detectors. So the probe that we're using, and I mentioned there's an HPT sensor. This is the sensor that's used to monitor the pressure of the water that's being injected. And then to this probe and sensor, we'll connect what we call a trunk line to that, and that goes through all of the rods. So here's another picture of that. So you've got your probe, where the connection to the trunk line is made. This is weaved through all of the rods, and then uphole, typically in a truck or a van or some vehicle like that, you will have the instrumentation, which is obtaining the data as we're drilling this into the subsurface. So we know that this is a string potentiometer, which is going to allow us to be able to keep track of the depth of the tool as we're advancing it. So before the operator begins the log, he's going to record the length of rods that we're using, and this will keep track of the depth. Now we're going to talk about a little bit more specifically about each of the sensors. So the electrical conductivity dipole, it comes in two different arrays. On the MiHPT probe, it's a dipole array. They both work very, very similarly. Very difficult to tell the difference between the two of them if you were to do side-by-side logs. HPT probes will have a one-air array, but basically we have a very small voltage, 0.75 volts AC, that we apply down to the dipole. It will travel through the soil to the body of the probe. So our two contacts are the dipole and the body of the probe, and we are taking a look at the ratio between the current and the voltage. That's getting multiplied by a constant and gives us our results in millisiemens per meter. So typically what we would see is lower electrical conductivity readings typically are sand. If you have a variety of EC response levels on your site, typically you're going to have more coarse grain. Sands and gravels are going to be lower, silts a little bit higher than that, and clays are going to be the highest level. What those levels are is very much site specific, and it is dependent upon the parent mineralogy of the soil. As well as EC is also impacted by any pore fluid that's present. If it's an ionic contaminant, something else that's could be adding more conductance to the soil, to the formation other than just the soil, that's going to show up as well in electrical conductivity. As I mentioned with the HPT tool, we actually have a water supply uphole, which is, and one of the controllers will set and regulate the flow rate of the HPT injection water. Downhole just above the probe is our sensor, and so we have a set flow rate, typically 200, 300 milliliters a minute, somewhere in that range on an MiHPT probe, and the system is trying to inject at that rate all the time. So depending on the formation we're in, the more coarse the material is, the more permeable the material is, it doesn't take as much pressure to inject that into the formation. The more fines you have, the more difficult it's going to be, and your pressure will increase. So here is a graph showing electrical conductivity. Again, typically the lower the conductivity, the more coarse material, typically higher permeability. As your EC goes up, typically your clay content would go up, your permeability goes down. So that's typically what we would see, but there are exceptions. Let me see here. Okay, and so with an HPT log, while the HPT log is being generated, we are going to be obtaining the data from the downhole sensor, and that's our HPT pressure data. There's also line pressure and flow, which is uphole, and then we can also calculate the piezometric profile, which will provide us with a static water level when dissipation tests are done. And then we can also calculate hydraulic conductivity, as well as, and I don't show it here, but we can also get an estimate in certain formations of groundwater specific conductance, which can be very interesting when you have an ionic contaminant. So here, in this case, EC is pretty low, and there's not a whole lot of change, but here the HPT pressure goes up, as well as here, a little bit higher than what it looks like over on EC. That could be a situation where you have some cemented sands or clays that just don't have the mineralogy to give us the higher EC that we would expect. On the flip side, if you have high EC that HPT doesn't follow, in this case, EC is going up. At the exact same point, HPT is not. It's still kind of a very low level, very easy to inject that water. In this case, this is an ionic remediation fluid that was impacting this log. So it actually, EC is going up and then drops to this baseline when HPT goes up and remains higher. So that's one way that and in this particular case, I could run some calculations in the software, the post-log software, and get an estimate of groundwater specific conductance. Moving to the MiHPT, here's the uphole instrumentation. So this is our MIP controller, which is going to control our carrier gas and heat of the probe, HPT pump and controller for that, and electrical connectivity is handled here, and we also obtain our data to the laptop. And then the gas chromatograph is here, and underneath this hood, this typically what most operators have are 3 detectors. The carrier gas comes in back here and first comes to the photoionization detector, which is a non-destructive detector, and then is split between an FID and XSD. And typically what we're able to see with these different detectors, we're having a continual carrier gas go past these detectors. So it's a total VOC analysis. There's no speciation or anything like that. We have the photoionization detector. It has a 10.6 electron voltage lamp. So any compound with an ionization potential at or below that of the lamp can be seen. That's typically aromatic hydrocarbons, double bonded chlorinated solvents. The FID is typically not as sensitive as the PID or XSD, but in high enough concentrations, any of our VOCs, any of our organic or carbon-based compounds will burn, and we will see a response on the FID if they're in high enough concentrations. And then the XSD is a halogen-specific detector, which responds primarily to halogenated compounds, chlorines, bromines, fluorines. Primarily in our environmental contaminants, it ends up being chlorinated compounds, but it will not respond to petroleum hydrocarbons. So if you have a corner gas station and dry cleaner, you're not going to see the gasoline contaminants on the XSD. So we can get some separation there. Detection levels, the systems, PID and XSD for say TCE, which I'm showing here, and say benzene, you should be able to, in standard MIP, be able to see less than 1 part per million, maybe a quarter to a half a part per million. They should be capable of in standard MIP. The FID is not as sensitive as at those lower concentrations, but it's able to see up. It extends a little bit further on the other side. So here are some examples of detection limits that should be achievable. The left side number is what should be achievable, but it just depends upon what a specific system is capable of doing based upon maintenance of detectors, you know, the age and where probes and trunk lines and some of the other components have been used that could influence and raise the detection limit on a specific system. So, but each system should be able to have detection limits like we see here in that quarter to a half a ppm range for a lot of these primary VOCs, gasoline-based VOCs and chlorinated solvents. Here are some higher concentrations. This is TC again. This is parts per million ranges, so 100, 400, 1280, which is the solubility point in water. And then NAPL, which in this case, I just took some straight TC and put it on sand, let out the liquid, and put that wet sand on the membrane. And you can see that here you have, you know, the stepped increase responses on the different detectors. This is not a linear response. It is up to this point for the most part, but once we go from the 1280 to NAPL, that's not even close to being a linear response. And you can see that here. So we're fairly linear up to this point, but beyond that, it's not. But it is increasing, so it will give a higher response to those when you do enter into a NAPL level. As you can see, the primary detectors I want to focus on here are the PID and XSD and the FID. So you can see FID is not as responsive on the lower end, but it goes up a little bit higher on the other side. So if we take a look at the data channels that we have, EC and HPT, and the 3 detectors, PID, FID, XSD, and in this case, since there's no response on the XSD, it's non-halogenated, PID, FID are responding, it's probably a petroleum hydrocarbon. And then I'm also showing a few other sensors that we record data for, and this is really primarily for the operator, but also for the consultant and regulators to take a look at the logs. It's something that's available to you when you get the raw data and open it up in DI Viewer. If the pressure, if there's a big pressure rise or pressure drop, that's showing that there's either a plug or a leak in the system, and any data from that point on may be compromised. And then also, what is the temperature of the probe? So we typically have it set to 120 degrees Celsius, and that if it's not there, we may not be getting a good a proper reading that we would be expecting. So as we get ready to do this, we do have quality control parameters, quality assurance measurements, chemical response tests, EC dipole test, HPT reference test. And then for QC, we really look at doing log reviews. Does it look right? Soil cores, confirming what we're seeing, either lithology-based or chemical-based, possibly doing replicated logs, not typically done, but could be done. On a chemical response test, we're taking a known concentration of, or a known standard, putting it into a solution, creating a known concentration, and exposing that to the membrane. In this case, we're immersing the whole probe into the solution, or you could take just a portion of the standard that was made up and expose that to the membrane in a vial. And here's an example of, this is a 4-level response, 1, 5, 25, and 100 parts per million. This allows us to be able to check the integrity of the system, make sure we can see at our lower detection levels, see that things are consistent before and after, and throughout before and after a log and throughout a project, so that we can be confident that we can compare this data across the site. But I want to make sure that you don't misinterpret. This is not a calibration. So the results we get are in microvolt readings. It's not in parts per million or parts per billion readings. So that's important to know. The best way to correlate that is to take actual samples and send them to the lab. So when we do a response test, this is I'm going to take a stab that this is, say, 5 parts per million of benzene. We have a certain response, and there is a certain trip time. When we expose the standard to the membrane, it's going to take some time to get to the detectors because of the length of the trunk line and the flow rate. We need to know that trip time so that this response that we see at the detectors will get plotted to the correct depth in the log. And that's something that's gone over extensively with operators, so they should know that, but it's good to understand that. We also have an EC dipole test that'll tell us if we're getting good data from that. And the HPT reference test will, we do go through this process to ensure that the HPT sensor can accurately measure a 15-centimeter column of water, so that in all these cases, we are confident before and after the log, the sensors are working and capable of collecting good data. When we are ready to begin a log, we're going to get the membrane at the ground surface and advance the tool approximately 2 centimeters a second until our first sample interval, basically every foot or every 30 centimeters, and we will stop for about 45 seconds to allow the heater to heat up, get a good sample across the membranes, diffuse a good sample across, and once that time's up, we will advance to the next interval. That also, once we pass through contaminants, it allows the membrane to help it to clear off, to desorb a lot of contaminants that may be sorbed to the membrane. So how do I know that what I'm looking at, or the compound that we have on site, is going to work for MIP? Well, some of the primary chemical properties that we look at are going to be boiling point, vapor pressure, water solubility. Also molecular weight, melting point, those are things that are easy to be found. We usually will go to Wikipedia, just obviously an easy place to end up when you Google search these. Sorry about that. You able to find the properties very quickly. And as we compare some of the different properties here, PCE and TCE, we see here that fairly low boiling point, lower vapor pressure, low water solubility. So that's going to be good. As we take a look at a few others, in this case, 1,1 DCE and vinyl chloride. Again, low boiling points. We've actually had some higher vapor pressure, which makes it even better to diffuse across the membrane, to volatilize, low water solubility. Benzene, also, same thing. Good candidate. MTBE, we're starting to increase that water solubility, so there are some things that the operator is going to have to do if it's specific, site specific, looking for MTBE or other what we would call polar molecules that are going to want to bond or bind with the water vapor that could be in the carrier gas. In this case, 1,4-dioxane, very soluble in water. It's actually rather difficult. It's going to have a very high detection limit. Honestly, not had great success with 1,4-dioxane, being able to see that, but you'd have to be in a extremely high concentration to be able to have an opportunity to see that. And then other compounds that are just not going to work, although we get asked all the time, PFAS, PFOA, those, no, it's just not going to work. Multiple things that are going against us here. Higher boiling points right here. Again, we don't have to be at the temperature of the membrane to diffuse through and get response, but the closer it is to the membrane temperature, again, and that's 120, that helps. But again, here we've got low vapor pressure on these, very high water solubility, as well as molecular weights and that. So those are not going to work. We do have on our website, and I believe it's one of the tech notes, a list of, there's a PDF list of various compounds. It's based on an EPA 8021 list of various compounds that are probably going to be pretty good, and a lot of their chemical properties, and if you can see them or not on specific detectors. So those are some good resources for you. As we look at some logs, we're going to take a look at, I think, 4 logs here and do a little bit of interpretation, then go into some site data. So here we have electrical conductivity and HPT pressure. Both are very low. As we're going down, very low HPT pressure, probably likely a coarse grain material. Here we have our PID and XSD. They both have the same pattern, very similar patterns here. And probably can't see it so well here, but the scales of these detectors are very similar as well, which is an important thing. Scale is important. You're going to see that later on. But so this is likely a double bonded chlorinated solvent, maybe TCE or PCE. And because we see it on it's a chlorinated solvent because we have it on the XSD, likely a double bonded because the ionization potential allows the PID to see it. Now, I can kind of see a trace of that in the FID as well. If we were to change a scale, we might see this profile in the FID, but there's also this response here, which does not show up on either of the other two detectors. This is likely methane that's responding, perhaps some that's been generated from the breakdown of the solvents that are there. Methane's not seen on the other two detectors, but very responsive on the FID. So on this log, again, our EC and HPT, where our contaminants are, it start to see it where there's higher EC and higher HPT pressure. So that's probably more of a silt or a clay, where we're starting to see that, and it eventually kind of comes down in that transition zone. So we may have it contaminants in the storage unit here, and then back diffusing out into the permeable zone. No response on the XSD, so non-chlorinated, likely petroleum hydrocarbons on this. Now, here's a log that's a little different for probably many of you, but this is still an MiHPT log, but this is a low-level log. I'm not going into the specifics on that, but basically it's a slug of response that we see, and it just shows up as a spike, and for lower detection limits. But we can kind of read it the same way. So up here, there does tend to be a little bit of a background on the PID, but we see there's some response up here. So without XSD response, probably some petroleum hydrocarbons. As we get down in here, we have our XSD responding. There's a similar profile here on the PID. So once again, probably a double bonded chlorinated on this site. Also a little bit higher HPT pressure in there, a little spiky, interbedded sands with the clays, but some similar ways to read that. And another low-level log, again, petroleum hydrocarbons near the surface, XSD response down below, and we see actually two different profiles here, but there's a couple spikes down at the bottom, but I'm not really seeing it over here on the PID. So I would suspect that since we're not seeing it on the PID, that this could be a single bonded chlorinated, not a double bonded. So maybe it's dichloroethane, trichloroethane, or chloroform carbon tetrachloride, something along those lines. Something with a higher ionization potential that the PID is unable to see. Okay, so now we're going to step into a couple different site examples here. So this is an old petroleum hydrocarbon site, an old gas station. The source area is out here, and we had done some logs and we did a log here and a couple samples, and I believe it's this one out here that we're going to be taking a look at. So near the source area, this is actually completely different, an OIHPT or optical image profiler. It's a fluorescence tool that we have, and at this particular zone right in here, we see that we did have some NAPL or residual NAPL in that 20-foot, 25-foot zone in there. And we're seeing the fluorescence image in that. So we're going to step out from there out into this area for the MIP. And there was a soil core taken. And this is where a couple of the MiHPT logs were done. And this particular log, we see the FID and PID response. The XSD is here, so there's no, is right here, the straight line. No response there, non-chlorinated petroleum hydrocarbons. Okay, so, and as I said there, no chlorinated solvents. So up in this, so the question, one question you have here is, we get this response, what's there? What's our concentration? Well, we're not going to give you a concentration because of all the variables that we have that are different from when we do our chemical response test for what's in the ground. So we can't just directly give a concentration to this response. So we're going to take some soil cores and send those off to the lab and see if this flat baseline is below detection limits. Of course, here we have response, so we know that's likely contaminated, and this is below detection limits. We are going to come back and take some soil cores, but also want to talk about it is common to see a bit of a tail coming out of a higher concentration zone. And what that primarily is due to is compounds that are absorbed to the membrane, especially in a gasoline site, petroleum site. There's hundreds of compounds in gasoline, many of them with much higher boiling points than what we're using for our response. We go from gasoline range goes from, if I recall correctly, I believe it's about 60 degrees Celsius boiling point, MTBs in that neighborhood, up to 218 for naphthalene. So our membrane is heated to around 120 degrees Celsius. The higher that boiling point, the more time it's going to take to desorb from the membrane, and it can take possibly a little bit longer getting through the trunk line. That's going to add to the tail. So question is it there or is it not there? Here's the two different logs, 05 and 06, and how they overlaid. You can see EC and HPT are very, very close. The detectors responded very well also on these, so very good correlation. So collected soil cores every 2 feet in these zones, trying to just confirm, is this non-detect, what's the concentration, and down below. So this is the results for this particular site that we had. Down to 22 feet, it was below the detection limit. Then we had GRO readings up to a little over 200 ppm, a little over 300 and 458 parts per million. And then 2 feet below that, we get back down to non-detect. So how does that look in the log? This is what, if we do a custom data set in the DI viewer, we can plot our concentration of response along with our MIP detector response and see how that shows up. So again, here we had non-detect and we had non-detect below there. So again, that kind of confirms that that is, all right, here's where I had my description for the tail. 55 to 100, 218 degrees Celsius within petroleum. It is going to take a little bit of time to clean up. And basically what I look for in these logs is when you're coming out of a higher level contamination or a higher level MIP response, if it's stair stepping down lower and lower and lower, you might get a spike, but if it steps down lower and then spikes and steps down lower, that's just a cleanup process of the contaminants that have been absorbed and just take more time or heat cycling to come off the membrane. Okay, and yeah, I'm not sure what, oh, so here we're just taking a look at kind of correlating between the OIHPT log and the MIHPT log. They're a ways away from one another, but you can see here, this is in this permeable zone on top of this clay. This is absorbed into the clay, and again, kind of coming out of there, maybe some back diffusion. Now in this area, when we take a look at a cross section of logs on this particular site, this is what we can have. Now, One thing that you can see here, this is closest to the source, and as we move away, in this particular graph, I have all of the detectors. They're actually um, graph scales were not synced. When they were synced, no, when the graph scales are synced, which is what you're seeing now, we can really see where the highest concentration is. So this last one was auto scaled, so you can see how much is in each particular log when you sync the scales and have a common high level response on the detectors. We can see our highest levels here, pretty high concentration there, a little bit lower in these zones. Now we're going to take a look at some data from a site over in Denmark that we worked on a few years back. This is from a town called Skutelev, which is about an hour west of Copenhagen, and it is certainly a glaciated region. Had a lot of glacial till with some other unconsolidated deposits. So some of the logs that we had done there, we'll take a look at. This is just some MiP logs. This is electrical conductivity. Again, we would expect lower EC would be sands, higher EC is clays. The PID and XSD, again, we see both of those are responding and very similar. So here, similar scales, and which is important to really understand what you have there. And then we did do also some conformation sampling. In this case, this was in a coarse grain material, so we're taking groundwater samples, and we had seen analytical data that included PCE, TCE, DC, and vinyl chloride. And the highest level was right here, 71 parts per million. If we take a look at the having this run out on me here, take a look at the HPT logs or sections here, electrical conductivity, HPT, the flow rate. We can see that, again, we have lower EC, coarse grain material in there, possibly some tighter material down below. And here is we had done some soil cores, and this is probably more of a coarse grain sand. In this area, we get into that till down below if we look at our HPT pressure. We were able to, so I haven't talked a lot about dissipation tests, but when you're below the water table, you will certainly want to have your operator stop and do some dissipation tests. Basically, they're going to stop the probe and go over to a time graph and shut off their water flow. And by doing that, they will dissipate off or bleed off their injection pressure, leaving you with atmospheric pressure and hydrostatic pressure for whatever depth you are below the water table. Then in the software, we can back calculate with that, get our static water level. And from this, we can also obtain our estimated K, which is corrected pressure, which is subtracting off. So leaving us with just the injection pressure. Our flow rate divided by this times a constant will give us our hydraulic conductivity. For the site in Skutelev, this is the overall site map, which we find very interesting. This was put together prior to us going over with the MiHPT. They had done a bunch of MiP work without HPT included on it. So they had EC data and detector data, but did not have the HPT data. So the plume snakes around like this. Groundwater flow is in this direction. So there's a few spots in here where it makes sense in the direction of the contaminant flow, but not so much right in here. Why why is it going in these weird directions? That's what they wanted to find out. And when we took the MiHPT over there, we had just added HPT to the MIP tool. Our goal was not to remap the entire plume, but let's see if we do a cross section from low to non-detect across the heart of the plume into this hotspot over here. What are we going to be able to find out? So that was kind of the goal of what our plan was. These borings were about 8 meters apart. And the first log that I had been showing was from this section right there, right on the edge of the plume. We're going to take a look at this SK04 log. And as we look at that, and we look at our electrical conductivity, we see that it's up here around 40 millisiemens per meter, but really does not have a whole lot of change. You can see the soil cores that were taken. You got a pretty coarse grained sand in this zone, and we have a clay till. Over here, HPT pressure does see a rise in, we do see a rise in the HPT pressure when we get to this point here. So that is kind of correlating with our clay. And then we do have some lower level contaminants showing up on our detectors down below, mainly in the tighter materials. And then when we step out and take a look, we've got this hotspot sitting over here by itself. When we take a look at that log, once again, we see electrical conductivity has pretty poor definition. Not able to tell a lot from that. Might be able to make some guesses, but pretty unclear. On the HPT, pretty low pressure in this zone, very sandy aquifer there, but then we have our pressure's going up in the clay till, and that's where our responses on the PID and XSD were. Very high concentrations there. So where does that leave us? We've got those logs. Let's take a look at the entire cross section of this and see what we can tell. So here we're going to take a look at our HPT pressure. Okay, so when you look at this cross section, east to west, left to right here, if we were to draw a line looking at the contact of the sand to the clay interface, kind of do that in your mind, and I'm going to help you out here in a second. Does it look like that? Okay, what does that begin to look like? What are we defining here first? Sand and gravel up above, clay till down below. Next question is, what does that resemble? Possibly a buried stream valley. Okay, I mentioned earlier that we have there in Skutalev, it's glaciated, so we certainly, as the glaciers receded, you're going to have meltwater that's going to erode away the clay till and deposit in the coarser materials that are carried along with the glaciers. When we substitute in our XSD response, we see that our XSD plume response is right in the heart of that. Now, is this all, we've got migration through the stream valley. Does this start to make sense now? How we kind of go, maybe not against the grain, but not flowing exactly with our known groundwater flow path in our shallower sandy aquifer. So, but there does leave us a question. What do we have here? Why do we have these high responses out here at SK12? Well, that's out here. And as was kind of shown before, it is somewhat connected, but you know, for a hotspot, it's out on its own. How did that happen? So we kind of went back and talked some more with the client that was involved. They pulled up some of the utility information, and when we laid that down, we took a look at it, we saw that we had sewer line connections at these points. So you had a sewer line connection basically on each corner of the north end of the building, which provides a hot spot here. We've got a leak in that connection. By the way, there's a leak out here, a hot spot, I should say, and that is the loading dock for this particular facility. So loading dock, sewer line connection, and then a sewer line junction. So now that's starting to make a little bit more sense. And also what's kind of interesting with this, since we're seeing this within this, contributed by the sewer lines are sitting in, a sandy or gravel pack. It's going to make a conduit to things that are downstream from this, which there are a number of homes. This is basically on the edge of a neighborhood. If I recall correctly, there was about 50, 60, 70 homes that had to have their sewer line connections redone because of vapor intrusion that was coming from the site. They didn't really realize it was coming from the site, but that's why, and obviously leading off into another direction. So, okay, so here, there's a question here. I had talked about a number of the EC logs where we didn't see a high response to the clay, but we do see a response here. What's going on with this? Actually, it's starting to go up here, a big response there, but comes down to a baseline and HPT goes up and stays up. So what's going on there? We had taken a number of groundwater samples, not one right in here, but to this point. And these are, I believe, 30 centimeter, 1 foot groundwater sample intervals. And groundwater specific conductance was rising as we were taking these samples. I believe we have, these are overlaid, so I believe our up to about 2,000 microsiemen per centimeter. This is about 1,000 microsiemen per centimeter. So we go about an order of magnitude from here to here. So what was causing that? Well, it is a chlorinated site, and on this back corner hotspot, they had done a sodium persulfate injection. So when they injected the sodium persulfate here, it goes down and moves out, or maybe we think. So let's take a look at a cross section of just these 6 logs here. And if we take a look at our HPT is this purple line with electrical conductivity, just the black line unshaded. You can see on the outer sides, there's not a whole lot of response, but on these inner 4 logs, we do see that response. So that would be an indication that that's where our sodium persulfate is running along the top of the clay layer. So once again, the high EC in this case in the sand is showing we're seeing that mapping of the distribution of the persulfate in the subsurface. So with that, these logs, EC, HPT, obviously the detectors, all of these can be, you can take this data, you can bring it into 3D models, modeling up the EC, the HPT, any of the detector data to really get a good handle of what your site looks like, in this kind of a perspective. And, that will basically, lead into really helping, with remediation design and doing that, which dropped down to the very bottom one. But in summary here for the MiHPT, detection of total VOCs, chlorinateds, petroleum hydrocarbons, methanes, dissolved phase plumes, even pretty low concentrations, even into the part per billion range. With low level MIP, we can even get a bit below 100 parts per billion, into the tens of ppb. The multiple detectors help us to identify different analyte families. We don't know specifics, we don't know specific concentrations, but we can break it down to the analyte families. EC and HPT really are key to helping us define our lithology and really understanding that. Contaminant data without lithology data is interesting, but you just don't have the context that you need to make the type of decisions that you guys are trying to make. So, and with all of these working together, we can really see where, identify if we're in migration pathways or it's sorbed into the clays and we've got back diffusion, those types of things. And it's going to help us in developing and implementing our remediation tools. So with that, I just also want to note that there are ASTM standards out there for the MIP and HPT tools. That's there are their designations for the ASTM standards. And turns out we ended up right on time.